So they do mention straight up to us that it's use instrument stack, and they just um, casually state that it's basically that you have to say that you keep on removing the last element per se. So I think the very first thing is they do mention that just very casually that last in first out. That's all we use that, very casually. And to me, whenever I hear that, I just feel like there's got to be more story arcs towards that, right? There's more nuance to that. So I think to do a counter argument is definitely look at the opposite side of last in first out per se. So I mean that um so the question now is like, what is the opposite of like last in first out? That means maybe say that I do need to play it out, and maybe play out on the left side. Let's say I want to maybe say delete a specific element, a specific index, and maybe this require me like maybe say a big O of like an operation, because I need to refer to the array. Maybe that's the opposite of it. And for last in first out, maybe it just do a very quick casual like a pop, and then that require me like a big O of one operation, very efficient. So maybe that will be the argument between Z and Y, whereby just Y simply having like the big O of n operation. You do need to know what index it is, and then you sort of like delete it per se. And I mean, the main concern is big O of n, because you go down to the specific index and then you have to actually delete that big O of n. Whereas for Z is that you just simply do a pop, and it doesn't even need to know much. Therefore just very constant time big O of time complexity. Maybe that's one of the argument that we can actually argue about per se. I don't necessarily feel that there was like a lot of like discussion with regards to what's the after conditions. I mean, they briefly talk about the before conditions, which they actually discussed about per se. I feel like the after conditions is so much, but they don't actually do much reference towards the problem statement per se, and they just kind of like do a lot of like explanation based on what he drew, and the only reference point I can get is based on the diagram that he do draw. So I mean, from how I actually see is that the rules that he actually set for himself when he was doing the reference drawing was that you started referencing from both the left and the right. So what I mean by that is that maybe say for this 5, it will look right and left. So if it look right, if it's something that is higher or equal length, it can pass us through. But say 6, right? Because 6 equal right, it can't see anything at all because this two is too short, right? So it cannot see anything. So therefore we stop the loop over there. As we can see, I think it's over here. So what they actually do is that they first say, okay, before we actually pop the value, we need to actually take reference from what is like the length of the index per se. So the length was like 3. The index from is 1 because it can't go back. So first and foremost, two things. You look towards the right, look towards the left. You look towards the right, you don't see anything, and then therefore you're gonna need to pop the value. So that's what right does, right? So we do maybe say additional points. So if say that you look towards the right, you got nothing, you need to pop the value. So before you pop the value, you do look at the left. You look at the left, if there's actually nothing, you actually keep the length equals L equals to 1. So that's what actually happened for this case. Look toward the right, nothing, I need to pop the value. I look towards the left, I see nothing, therefore I determine the length to be 1. So I account the max area to be 6 times 1 because the height of 6, and then multiply by the length once, so therefore the 6 over here, right? And I account maybe say my previous has like a value of 2, so therefore I kind of like remove it because my new area will be the max area of 6. Just say if this 10 doesn't exist. So in some sense we somehow got thrown into doing the playout series, but it is what it is. So maybe say we look at maybe say maybe say the 1 per se. So right, so 1, I look right, maybe I say that I look 5. Okay, so I look right, it can go through, but after this one I can't look anything further because this is the 2. I mean, the moment this 2 is planted, it causes a lot of trouble. It causes trouble for the 6, it causes trouble for the 5. Not so much on the 1, not so much on the 2, but I think this kind of causes a ripple effect. The moment this is gone, this is also automatically gone. Let's see. Let me think. So maybe I just feel that therefore it will cause like a ripple effect towards the C. So ripple effect towards the last stack value, which is for 5 per se, and we kind of rinse and repeat for A and B operation per se. So we look towards the right, we actually do have like a value per se. So maybe we do like some form of like counter argument per se. So we look towards the right, there's a value. Thinking. I feel like maybe say that the moment we hit until 2, we got to look at the towards the right, that is all the way to the very last element per se. And if if that it's empty per se, you kind of like pop the value. But then the next step I think for this will be that you actually do have to actually go look at the right again. This time around it's not all the way towards the edge, which is where the 2 is. It's so much more about like securing your finding out about your area per se. So if there is, for this case there is values and it's until this area, so therefore your length will be incremented accordingly. And now the next thing is that you do look at towards the left also, and for this case there isn't any value, so your L just remains not being able to actually plus, right? So that's pretty much it. So we are during our right positions, we are actually able to increase by once per se. So the L suddenly becomes 2 times 5, we get a tenth. So with tenth, this now becomes our new max area. Our previous was a 6, we kind of like remove it, now we have the new max area. So for the 2, we kind of like pop it and pop it for both the index and the heights. I think at the end of the day, what we want to do is do maybe say at the end of the day, do a comparison between the after conditions and the before conditions. So from how I see as of right now was that I do I do see that we pop the value, it's always the last value per se, right? For both cases, so this was like case 1 and this is case 2. Both cases share the similarity of like popping the last element, and that kind of like coincide with the before conditions, which is the last in first out. So I think that leaves us a clue of like using this instrument of stack per se. So that's the thing that I'm getting so far. So but we then move on, talk about playouts. So maybe we after here we come here. So 2, we first look at towards the right. So this time round, it's a nice situation because we look towards the right. Say there's it passes. We don't need to do actually anything. We don't need to do the popping, which we usually do, and we don't need to carry out B and C at all because we didn't pop any value. But once we enter the realm of like 3 per se, suddenly we see that, oh, we look towards the right, there's no actually values anymore, and this one is actually at the end of the values. So I'm not sure how they know it's at the ends and how they're gonna like move on from there per se. But just let's say that they do know how to actually look at it and they move on to the next operation. I think which they did is to move on to the L operation over here per se. So they do know that that 3 still exists, the full 2 still exists, and left the 1 still exists, and they're gonna like do the final calculation for it. So the similarity for this is for everything, because you know you reach the end. The moment you reach your end, that means all your area, the end of like the calculation will be at this point over here. So no matter what, both the 3, all the elements 3, 2 and 1 will end of the area to be over here, right? So for 3, I just start calculating first. For 3, which is the last element, which is this whole entirety of the area, it will be 3 times 1, right? Intuitively speaking, based on the index, I know the length, and then I already know this thing is a 3, so area is 3. Is it bigger than 10? No, so I don't include it, right? So it's a 3, and then we calculate the next ones all over here. So it's a area index coming from so this one is actually belongs to 2. The thing was that it can look left and it can go all the way until here and look right all the way towards the edge. So first thing first, it look towards the right, it does reach until towards the end, and not only it need to look towards the left, it also need look towards the right, it also need to look to the left. So if you look to the left, it get bottlenecked by the basically you need to consider the height of the item, right? So for the item, there's all the taller ones. I see. So for this case is that they look towards the first condition. So I think when we look towards the right, what we actually looking at the overall grand scheme of items is this, that I want like a taller height area. In every single thing we're just considering if there's a taller height area. That's our condition sets. So for 2, this case is 6 and 5, all 3 is all like within the area. So we take out all this area over here. So with that, we got 1, 2, 3, 4, and 4 times 2 gives us 8. And for the very large edge case was that once you exist, we look towards the right sides. It can actually reach until all the way towards the edge, as we mentioned about, which is 1, 2, 3, 4, 5. And we look towards the left, we still can continue by 1s. So it's a 6 times a 1 and gives us a 6. And that gives us the final result for everything. And all of this is not comparable to a 10. So 10 is our final record that's sent back to the results. Very interesting, very interesting. We do something that we miss out. But I mean, it was like very intuitive for us to actually think about these first steps first, and we already do at the back of head, we do know it's like the need to be the taller height for us to be able to take it into consideration or not, right? I mean, with everything being said, I think we always have to actually do come down to actually talk about the brute force, right? At the end of the day, we still need to talk about brute force, right? So for brute force, I just believe that maybe it got to do with why per se, because I mean, if you aren't using a stack, you'll be using a normal element per se, and we kind of like discussed that at the end of the day it does requires a big O of n operation per se, and that contribute to the complexity of every single thing. So that's what I believe. Interesting, we actually did discuss about brute force. But with that being said, I think that's it. Yeah, everything comes to an end.